Hi everyone, welcome to the last session of Biodynamics Days 2023. It's our great pleasure to have today Bjorn BIRNIR from the Center for Complex, Nonlinear and Data Science of great pleasure University Santa Barbara in California. And he will talk about stochastic closure in Lagrangian turbulence. Thank you, Bjorn.
Thank you. I want to thank Benjamin and the organizers of the conference to invite me to give this talk. And this is joint work with Luisa Angeluta, who is at the Njord Center in the Physics Department at the University of Oslo. And here is an outline of my talk. Give me for a second. I'm fighting here with the computer. Okay, there we go. Yeah. I need to tell you a little bit about the deterministic versus the stochastic Navier-Stokes equation. We're going to use the stochastic Navier-Stokes equation as our model. And the first problem that I would like to tell you about a little bit is homogeneous turbulence. We're going to use the Reynolds decomposition, and I want to tell you about the improved closure model that we have there. Then I need to tell you a little bit about boundary value problems. Something called the spectral link that allowed us to model the boundary value problems. There's a lot of activity in pipe flow and so on, and we were able to model that and got good results using this idea. That actually came from the University of Illinois. And then we'll get to Lagrangian turbulence, and I'll tell you about the theory and the simulations that we got from Biferali's group at the university in Rome. And then we'll have some conclusions. So let's start with the deterministic versus the stochastic Navier-Stokes equation. So here is the Navier-Stokes equation with the incompressibility condition. And what I like to do is that I like to eliminate the pressure using the incompressibility, because that shows that there are really two nonlinearities in the equation. One is the usual inequality from the inertial terms, but there's another inequality coming from the pressure terms as well. And that actually plays a fairly big role in the theory. And the turbulence is quantified by the dimensionless Taylor-Reynolds number, which is a typical velocity in the flow, the correlation length lambda divided by the pneumatic viscosity. And I'm going to be talking about the situation where the Reynolds number is fairly large. So I'm not going to be talking too much about the transition to turbulence, but we assume that the flow is already, fairly turbulent because we have a large Reynolds number. Now, what one can do is that you can apply the classical Reynolds decomposition. So you can decompose the velocity and the pressure. And then we get the classical Reynolds model or runs for the large scales in the flow. And the last term there is the eddy viscosity, where R is the Reynolds stress, and that describes how the small scales in the flow influence the large one. And the closure problem that I want to address by using a stochastic equation is to compute, the Reynolds stress. So the large-scale flow has this form. The small-scale flow now is the usual Navier-Stokes equation with the two nonlinearity with noise. We're going to add the noise to the Navier-Stokes equation. Now, this is not a new idea. In fact, if you look in the book of Landau and Lifshitz, that was published in 1959, then they argue that the proper model for turbulence ought to be a Navier-Stokes equation with noise. And the noise that they proposed to add was white noise, both white both in space and time. Now, the problem with that was that it was shown about a year later that if you have white noise, if you drive the Navier-Stokes equation with white noise, you get a solution which is not a function, it's a distribution. And it's not continuous in particular, and there is little evidence that we have discontinuous vector fields in nature. So the question then becomes, what should this noise look like? If we can't use white noise, what does the noise really look like? What is the form of the noise? And as we will see, it will contain both additive noise and the multiplicative noise. And the idea is that why do you have this noise? Well, that's because once you make the transition from laminar flow to turbulent flow, then the flow is unstable. And what that means is that the instabilities in the flow, they're going to take the ambient noise, which we always have in any fluid, and they're going to magnify it. In laminar flow, it's quelled, you don't have to worry about it, but in turbulent flow, it's magnified. It becomes a non-trivial noise term, and you have to include it. But the question is, what does it look like? And here is our proposal for what it should look like. This is the equation now for the small scales. It has a contribution from the large scale velocity, but you can see that I've written it as a stochastic PD now, and there are three terms in the noise. The first two terms are additive noise, and the third one is multiplicative noise. And the additive noise can be written as a Fourier series with some coefficients, CKs, which are decaying. And then every Fourier components, the EKs are just, the usual Fourier components. And I'm assuming that we have periodic boundary conditions. That every Fourier component has associated with it a Brownian motion. And these are independent. So we have basically infinitely many Brownian motions, which are driving the different Fourier components, and the CKs are decaying so as to, make this expression, this noise, make sense, in L2. The third term, and I should say that the way you derive this is that you use very standard arguments. And basically what this is that the first term is the mean field contribution of the noise. And you make standard argument that it doesn't really matter what kind of noise processes you have, the mean field is going to give you Brownian motion. And we're using, standard arguments in probability theory to derive this term. However, you get something more than the mean field. And this is also well known in probability theory, that we're going to have deviations from the mean field, especially if we have a bias in the equation, and the inertial term gives us a bias in the Navier-Stokes equation. So we're going to have deviation from the mean field, and these deviations, they are given by the large deviation principle. And that's what the second term is. That's what the second term is. It's basically adding the large deviations, to the mean field. How about the third term, the multiplicative term? Well, we know that in three-dimensional turbulence, we're going to have vortices, and associated with these vortices are jumps. So the third term is basically modeling the jumps that we get, when we run into these vortices of different sizes. And this is a finite series. M can be very large. You can have a large number of vortices, but we have a finite sum with the size of the jump, which is hk, and then n is a number process. It's a Poisson number process that tells us the number of jumps associated with the kth Fourier component. So that's what a model for the noise is. And the arguments that one uses are general arguments from probability theory, which means that this noise that we put in is generic. It's just the generic noise that you would expect to have. But the problem is that we have, infinitely many coefficients, CKs, DKs, and, finitely many HKs. And we have to try to figure out what these coefficients are. Okay, now in 41, these two gentlemen, Kolmogorov and Obukhov, they proposed a statistical theory of turbulence. I'm sure you all know this, but let me review it anyway. The structure functions of the velocity differences of a turbulent flow, they should scale with the distance or the lag variable between them. If you look at the velocity at 2 points and you compare them to a power, p/3, where p is the pth structure function. Basically, the argument was that if you look at the moments in turbulence, they're rather boring. They're Gaussians with some flatness and skewness. So if you want to get at the interesting structure, you have to look at the structure functions or the velocity differences, and then you get this scaling, which is different from a Gaussian. And they proposed that the structure functions, expectations of these differences, should scale with some universal coefficients, and then the lag variable L to the power p/3. And this, of course, was criticized immediately. Landau, he pointed out that the coefficients or the constants, they couldn't be universal. They had to depend on what fluid situation you were looking at. And they were also criticized for not including intermittency. And there was quite a bit of evidence that intermittency is important in turbulence, and this people have understood this even better since then. So in 62, they came back and proposed a refined similarity hypothesis, where they take into account the energy dissipation into the flow, and that's going to contribute to the exponent of the lag variable. So you get a new exponent, zeta p, and the scaling exponents, it's the old exponent, and then the intermittency corrections. Now, Kolmogorov proposed that these are log normal, that the intermittency corrections ought to be log normal. He used some studies that he had done of milling in a mining process. That turned out to be not correct or inconsistent with observations. And it wasn't until in the 90s that people figured out that these are log-Poissonian processes, and the form of the correction was worked out by She-Leveque. And of course, the coefficients CP are not universal, but they depend on the large flow structure. So the question is, can we now use our stochastic closure theory to prove Kolmogorov's and Obukhov's theory? And let me categorize, what we're going to do. We're going to take the turbulence problem and we're going to split it into homogeneous turbulence, which is presumably the simplest situation. Then we have boundary value turbulence, including pipe flow, where we really have to take into account the effect of the boundary. And finally, we have Lagrangian turbulence, where the fluid is possibly carrying particles which are distributed. And in the first two cases, we're going to use the Eulerian description, where you stand and you see the flow by you. And in the last case, the observer follows the fluid, and he or she follows the fluid particles. So we're going to briefly outline the stochastic closure theory of homogeneous and boundary value turbulence, to give you a little overview, and then we'll come to the closure theory of Lagrangian turbulence, which now is mostly developed, even though it isn't completely published yet. And I'm going to spend the rest of the talk on that. So let's start with homogeneous turbulence. Now, it turns out that you can use the stochastic closure theory to compute the structure functions. That's a little surprising, but it turns out that using this stochastic equation, you can actually compute the structure functions. And if you compare the theory with observations and simulations, then the theory is the red line, and there are some experiments which are the black disks. There are simulations which are the circles, and then there are high Reynolds number experiments done in the atmosphere, which are the crosses, and they fall right on the line. And the blue line is the Kolmogorov-41 scaling, for comparison. And as you can see, we do very well in reproducing the experimental and simulation results. This is what the structure functions look like. These are the first two. And I had a student, John Kaminsky, who was actually able to work out the Reynolds number dependence of the structure functions. So you can see the viscosity in there, and that's where the Reynolds number dependence comes in. So we could, these are the first two structure functions, but you can write down a formula for all of them. And we used data from the Max Planck Institute in Göttingen. That was Bodenschat's group. They have a wind tunnel that where they made measurements with different Taylor-Reynolds numbers, and we compared the structure functions, from their experiments with the theory. And this is the result, that here you see the structure functions as a function of the lag variable. This is the second structure function, and this is the same on a semi-log scale. And as you can see, is that the red line, which is the theory, compares very well with the simulations. And this is true for the higher structure functions as well. This is at low Reynolds number. And then if you go at, a much higher Reynolds number, you still see a very good comparison between the theory and the experiments. And you get the structure function as a function of the lag variable. Okay, so that gives us some confidence. So once we have this comparison, we can try to figure out what these coefficients are that we wrote down in the original noise. So when we do that, then we can compute the correlations of the noise. And what we see is that for a small Reynolds number, the noise is very peaked. It has a sort of a sharp correlation, has a sharp corner. But when the Reynolds number gets very large, then it's oscillatory, and that's the picture here on the right. So what the noise is doing is that it's trying its best to be white. It can't quite be white because that would give you a distribution, but it's oscillatory, and the oscillations, they are getting as close to white noise as they possibly can. So you get something which is localized, for low Reynolds number and highly non-local for or large Reynolds number. And that's what one would expect. So you can then go back and you can put this into the model. You can compute what these coefficients are. And it turns out that instead of having infinitely many coefficients, we now just have 4 parameters. It turns out, well, we have 3 parameters in these equations. There is one more in the structure function, and they are these coefficients, and then the power, of the Fourier, variable. And all of these, these 3 coefficients in the model of the noise are functions of the Reynolds number, and we know what these functions are, from our comparison with the experiments. So now we have a much simplified model for the noise. We can compare this then with the PDFs of the velocity differences, and we get, a fairly nice comparison with the experiment. The experiments are the blue and the theory is the red. It turns out that the PDFs are what are called generalized hyperbolic distributions. We can prove that. And they compare well with the PDFs, at least if you don't go too far out in the tails, and we can come back to that point, later on. So can we now take this theory and we can use it to solve boundary value problems as well? The answer turns out to be yes. These 3 gentlemen now developed that theory. That's Pratt, von Karman, and Taylor. And they discovered that the turbulent boundary layer could be divided into 4 sublayers. Again, I'm reviewing what you probably all know. There is the viscous layer, which is closest to the boundary. There's the buffer layer, which is a transition layer, where you go from the boundary layer to the scaling layer. And then there's the initial layer where you have scalings. And then furthest from the boundary or in the center of the pipe, you have the wake. Now, Pratt and von Karman, they wrote down the famous Pratt von Karman log law, which applies in the inertial layer. So you basically have the velocity scaling with the distance from the boundary. Y is the distance from the boundary, and tau is called the friction velocity, which is based on the wall stress, and K is the famous von Karman constant, and B is a constant that varies from, from experiment to experiment. So this was the theory. It was a great success, and it was used to build the wind tunnel and develop aircraft. But the theory got stuck there. And it was basically stuck until in 1956, this gentleman, Alan Townsend, an Australian, came along and proposed his theory of attached eddies. And what he said was that the way that momentum was brought from the boundary into the fluid was by a hierarchy of eddies that were attached to the boundary. And then he used this hypothesis to show that if you look at the fluctuation or the velocity deviation from the mean, and you look at the streamwise component, then that also satisfies a log law. And this was later verified experimentally by Perry, and these coefficients, D and A, they are called the Townsend-Perry constants. And then later on, people came along who were studying pipe flow, and they proposed a universal log law for all the moments of the fluctuation, and with new constants, but the y plus is the distance from the boundary, and these new coefficients, dp and ap, they are called the generalized Townsend-Perry constant. So the question is, what this indicates is that the Kolmogorov-Obukhov scaling is dominant in the inertial layer, and then there you get the scaling given by the log laws. But people discovered that the generalized Townsend-Perry constants are not Gaussian. The model to derive them was basically the Gaussian model, but it turns out that they are sub-Gaussians. So the question is, can we do the same thing as we did for homogeneous turbulence and compute all the Townsend-Perry and generalized Townsend-Perry constants? That turns out to be the case. This was with a postdoc, and then it was verified. Then we looked at the experimental situation with She-Leveque. And here you can see the gray is the Gaussian theory that was originally proposed, and these are the normalized. What one does is that you take the higher coefficient, you normalize by the first one. Now, the stochastic closure theory are these triangles, and you can see that it gives you a sub-Gaussian behavior, and the circle that's inside the triangles are the experimental value. And this was done at very high Reynolds numbers with in the fluid physics facility at the University of New Hampshire with She-Leveque's group. So we were able to use the theory to derive these coefficients and compare with the experimental results. Now, can we do more? Can we actually get the mean flow and the deviation across these different boundary layers? And we saw that the stochastic closure theory could give us the fine structure in the inertial layer, but can we find the structure in the viscous buffer inertial layer and the wake? The wake is basically a model proposed by von Karman, and that holds up quite well. But let's see if we can, use the theory to get both the mean flow and the fluctuations in the or the square of the fluctuation in the different layers. And here is the answer. It turns out, yes, we can compute the mean flow. That's the black line. It sort of goes to 0 at the boundary, and then it increases and becomes, linear on a semi-log plot in the inertial layer. And the variation shoots up in the buffer layer, then comes down to almost a constant, value, and then decreases linearly as it should with the log law in the inertial layer. And what we did here was to use these ideas of a group of physicists at the University of Illinois, and Louisa, she brought this to our attention. This group, they had found an expression for the mean flow using a spectral function. Basically, you look at Townsend attached eddies and you derive a formula for their amplitude. And this formula is given by a spectral function where you have incorporated both the Kolmogorov-Obukhov scaling, which is the the 5/3 in the Fourier spectrum, negative 5/3. You also include the von Karman's decay in the wake, and with this spectral function, you can get the amplitude of the attached eddies. And when we put this into the theory, we get the right thing, except we don't get this flat, region in the buffer layer. And what we have to do is that we have to include a different form of eddies in addition to Townsend eddies. And we call these eddies detached eddies. So he had attached eddies, and we have, in addition, detached eddies. And they have a different scaling. And the way you can think about the scaling is that it's simply an eddy that is, speeding up and becoming narrower. It's just like an ice skater on ice that is spinning and pulls in their arms, then they speed up. And this scaling turns out to be, 1/k. The energy is basically constant. You're speeding up, but, your energy is constant and it's getting longer. And in Fourier space, that's 1/k scalings. Now, when we incorporate this into the spectral function or the spectral link, then we get a good comparison with experiments. Here is the comparison. Here is the variation, and the theory is the black line. There is some difference for the first coefficient, A2. But that's well understood. That has to do with the mean of the first structure function. We use the structure function from homogeneous turbulence to compute these coefficients. And for all the higher structure function, there is very good, comparison with experiments. And here we have, compiled a very large number of experimental results to compare with the theory. Moreover, this group in Illinois got a nice model of the mean flow, and here is the mean flow. This is the distance from the boundary, and the mean flow increases, and they got a good comparison. The theory is the black line, and all the experimental results on a semi-log plot are the dots with different colors. But it turns out that to get a better results, you also have to include the detached eddies. And their result is on the bottom, and our result is on top. And you can see that once we include the detached eddies in the buffer layer, we get a closer fit, to the experimental result. So they're both the attached and the detached eddies contribute to the mean flow. Okay, we are done with boundary homogeneous and boundary turbulence. I didn't go into the details, but we used the structure functions for homogeneous turbulence to compute these generalized Townsend-Perry constants for the boundary turbulence. But now let's see if we can use what we have, the tools we have, to understand Lagrangian turbulence. And the gentleman who made a significant contribution there was Richardson. He discovered the super diffusion or that, if you look at particles which are carried by turbulent flow, like from a smokestack, then for a little while they are close together, and then there's a super diffusion, and if you look at the separation of the particles, it grows very rapidly. In fact, it grows like the time, from when they emerged. The separation squared goes as t to the third, and this is called, Richardson super diffusion. Now, he discovered this by looking at weather balloons, and he estimated the diffusivity to be this function, where epsilon is the energy dissipation and r is the separation between the particles. Now, that implies that the separation squared goes like t cubed. Epsilon is the energy dissipation. And if you look at this experimentally, then the straight line, the straight line is the t cubed law. And if the particles are very close together, it takes them a little while to approach this super diffusion. But if they are further apart, they go quickly, to this super diffusive case. So, this is well supported by experimental evidence. Now, Obukhov actually gave a derivation of Richardson diffusion. He used the Kolmogorov-Obukhov theory to derive it. So here, he basically said that the diffusion constant ought to be proportional to the second Lagrangian structure function. And the Kolmogorov theory then says that goes as r to the separation to the power 2/3. So you can write down a differential equation. The average, so the diffusion coefficient is proportional to the second structure function and the eddy turnover time. And then when you plug that into the differential equation, you solve it, you get exactly the Richardson diffusion. So it results from the Kolmogorov-Obukhov theory, if you will. Now, in addition, there is a ballistic regime in the beginning, and that was derived by Batchelor. And in this regime, the particles, they separate linearly in t, depending on the initial velocity. But Obukhov derivation shows that the Lagrangian structure function holds the key to the statistical theory of Lagrangian turbulence. So the question is now, can we compute the Lagrangian structure function? So what do they actually look like as a function of time? And here we used simulations from Biferali's group in Rome. And you can see on this very nice, plot where the particles are separating, that you have this ballistic region in the beginning, then where the circle is, the super diffusion sets in, the Richardson super diffusion, and the particles, the separation grows rapidly. But then later on, something else happens. The particles, they get involved with the eddies, the turbulent eddies in the flow, and they begin to diffuse more slowly but more irregularly. And the speculation here was that in the beginning, you have this ballistic region, then you have this super diffusive Richardson regime, but then there's a transition from Lagrangian turbulence to Eulerian turbulence. And basically what's controlling the separation of the particles after the Richardson regime is the Eulerian turbulence, because you're basically, looking at a situation where where the particles are being separated or entrained in Eulerian vortices. So we would like to see if we can see this both in the theory and the simulations. And here are the simulations. So we are looking at the structure functions here. This is the, let's see, that's the, I think this is the fourth. I can't quite read this, but I believe this is the second structure function, just normalized by time. You know, you think that the second structure function in the Lagrangian scaling should grow like time. So if you normalized it by time, you would expect a constant, and you see there is some semblance of a constant, you know, at least for some times, some time intervals. But this is the structure function, and I believe this is the fourth normalized by the second and the sixth normalized by the second. And a good way of trying to get the scaling is actually to look at this derivative where you differentiate the log of the pth structure function with respect to the log of the second structure function. And what you see is interesting, that you start with the Lagrangian scaling, but then you dip down, you know, to a valley, and then you increase again up to what seems to be an Eulerian scaling. So there's a passage from Lagrangian scaling into Eulerian scaling, but this dip is very curious. You know, what is really causing this dip? Why doesn't it just go straight from Eulerian to Lagrangian? So what we did was to model then the structure functions, and we model them by assuming that they adhere to the Eulerian scaling to begin with, and then there's a passage over to Lagrangian scaling, and at the very end we assume that you get a constant. And the thinking here is that you see the Eulerian scaling to begin with, then you have a transition over, you have the Lagrangian scaling to begin with, then you have a transition over to the Eulerian scaling, but at the very end, these detached eddies, there are no attached eddies because there's nothing to attach to, but the detached eddies are there, just like they were in boundary flow. And they give you a constant scaling. So at the very end, you're basically being entrained in these detached eddies, and you're getting a constant scaling. That's the model. That's the theoretical model. And as you can see, that seems to give a pretty good result, but we really have to test these derivatives. And here I'm testing the derivatives. I'm testing the derivative of the log of SP, but with respect to log of t, not log of ST. And I'll tell you why in a second. And what you can see is that you get a nice transition from Eulerian scaling over to Lagrangian scaling, and this happens, for all the structure functions. So there is no dip. And in fact, if you compare the fourth structure function differentiated with the second structure function and just differentiated with t, you see that the dip is simply caused by the second structure function. And that means that what's happening is that because we are normalizing with the second structure function, and this is something that has traditionally worked in turbulence, you get a dip, but if you don't do that, you just normalize with time, which is the variable that you're looking at, then the dip disappears and you're in good shape. Now, as you can see also here, is that at the very end, you are getting something linear, which looks like a constant. And this is a typical trajectory of a particle once you get into the Eulerian turbulence. And we believe that this is showing that, you know, the particle caught in one of these detached eddies, which are sort of controlling what happens at the very end. Okay, let me give you some conclusions. So these Lagrangian structure functions, they can be computed by the use of the closure, stochastic closure theory. They exhibit Lagrangian scaling without intermittency for an initial time interval, but then they pass over to a regime with Eulerian scaling, which now has intermittency. That's how you get the right scaling exponents for a large time. And the time interval of ultimate decay is controlled by the scaling of these detached eddies, analogous to the scaling in the buffer layer of the boundary layer turbulence. And the dip that was observed in the log derivatives of the structure functions with respect to S2, the second one, is artificial, and it's just caused by the time scales which are probed by S2. And here is the observer, you know, looking at turbulence in the River Arno. Thank you.